All right, today we're gonna cruise through the linear momentum, the momentum equations, specifically the linear momentum equations. So we're not doing angular momentum, although we could, we might. Okay. So to just remind ourselves, last time we derived the integral form. So momentum balance or momentum conservation. Okay. So we had the dmu by dt for the system. That was equal to the summation of external forces. And we translated that using the Reynolds transfer theorem. That gave us the integral over the control volume, d partial by partial t, rho u dv, plus integral over the control surface of rho u dot n ds was equal to the summation of forces. Okay. And again, these forces don't care whether you're Lagrangian or Eulerian, because we're going to look at the system as it coincides with the control volume. These are external forces on the system. We listed some of them last time for forces. Okay, we had the volume forces, which were gravity, magnetism, etc. And we had the surface forces. So the volume forces act on the entire body of the fluid element. Okay? They don't distinguish one part or another. Okay? And we're not talking about fluid elements the size of an atmosphere where, you know, the distance is so large that the gravitational pull, you know, becomes a little bit different at longer distances, right? So for surface forces, we had the pressure and then friction. I love that word. Ali told us that word, friction, because it tells you, it enforces the idea that your fluid element or your control volume, you know, once you take it out of the fluid, it has forces acting on it on the surface, normal, also tangential on it, right? Because the other fluid elements are acting on it as well, so they're going to shear it. There's friction going on over here, right? It's, you know, rubbing on it. And then there are the volume forces that, you know, act on the entire body. Okay. All right. So I'm interested in gravity, in this case here, pressure and friction. We're going to write those out. So now we need to find expressions, preferably in an integral form, to put in here on the right-hand side. Remember, the integral in the integral in this form, this only helps us in determining external forces on kind of a large system like we did last time. What is the thrust force, for example? But, you know, further study of fluid mechanics is going to require us to know point-wise what's happening in a pipe, for example, flow over a backward-facing step, you know, flow in a nozzle. To do that, we need to get to the differential form. To do that, we need to express everything in terms of an integral here, and then rip out the integrand out of the integral, and bam, we get the differential form, okay? So I want to try to get an integral representation of these external forces, okay? So let's start with gravity, okay? If you take a small element of volume delta V and mass delta M, then the force of gravity, infinitesimal, is delta Fg is equal delta M times G. correct? That's the force of gravity, right? Acceleration, mass. So force is mass times the acceleration, okay? Now, the total force of gravity acting on the control volume or the system is simply the integral of delta Fg dV, which is equal to the integral of delta mg dV. Now, delta m is equal rho, which is fixed. Here, constant, we're assuming it's constant, delta V, correct? Sorry, integral of delta Fg. There's no dV over here. Apologies. Yes, delta mg, and that's where you get the dV from. So you get integral of rho g dV. That's the force of gravity. Gravity gives us integral over control volume of rho g dV. It's all in vector form, right? Which is good because this is a vector equation, UVW, right? And this gives us, if you have, gravitational acceleration in all three directions, right? Or some type of acceleration, you're orbiting in space, doing something in space, you might have acceleration in different directions, okay? Pressure, we already know that. That's integral minus over the control surface of minus Pn ds. I kind of gave you that answer in the homework assignment. It's simply, we know the pressure always acts at any point. It puts pressure on a surface. So it's always acting inwards like this. And the total pressure force over the control volume is simply the integral minus Pn ds, n is the unit normal, okay? Now what about friction? I'm gonna say we don't know what friction is right now. We're gonna worry about friction later. So all I'm gonna do is put an integral over the surface of n tau ds. Forget about what that means, just take it as it is, okay? And dot tau. We're gonna learn later that tau is the stress tensor, the viscous stress, the friction stress tensor, okay, from due to viscosity. But just write it in this form or call it F friction, okay? I don't care. Guess what? We're gonna neglect it for the time being because we're gonna deal with inviscid flows right now. So when you plug everything in, let me see how I wrote it here. Okay, good. You get d by dt integral of rho u dv over the control volume plus integral over the control surface of rho u dot n ds equal to the summation of forces. We get integral of minus p n ds over the control surface plus integral or friction force n dot tau ds. Again, friction is a surface force, so that's why it's a surface integral, plus integral of rho g dv over the control volume. And that's the general linear momentum theorem for a fluid. That's the general linear momentum equations. Well, vector equation. Okay, excellent progress so far. We are gonna neglect friction. Now, because friction in a fluid flow is caused by the action of viscosity, by neglecting friction, you're essentially dealing with fluids that are not viscous. which tells us that we call that inviscid flow. Okay, so when you neglect friction, tells you you're dealing with inviscid flows. Okay, are inviscid flows realistic? Okay, why don't you form into groups and chat about it a little bit? Are inviscid flows realistic? Can they happen in nature, or is it just an idealization? All right, I want to hit some chatter. Give you about a minute. So flows that don't have viscosity in them. Think about, when does viscosity go away? Okay, from your chemistry, from your other chemical engineering, what affects viscosity? Pressure, temperature, okay? Think about that. So yes, viscosity is a property of the fluid, but a flow condition could change it. Think what changes viscosity. What happens to viscosity when things get hot, when things cool down? And does it happen in reality? And where would it happen in reality? And no Googling. No Googling. If you use Google, I will ask you to derive the equations of... All right, do we have any answers? Any thoughts? Only the ideal gas? But is ideal gas realistic? So you're saying inviscid flows are not realistic, don't exist. Okay. All right. So actually, this would be cool to take a vote on this. Okay. Are inviscid flows realistic? Are inviscid flows realistic? Okay. Yes. No. So we got one vote for no. You said no? He's undecided. You're undecided. So you said no. Why? that's that's very kind of you. So why do you say no, Sam? Friction between the two. Okay. You got another vote for no. Okay. Ali and Hafiz. Yes and no. So you voted yes.
I feel maybe anyone is very close to it's not like a bubble.
Okay.
You have a flow kind of going in the zigzag manner. Inviscid flow might be possible.
Okay. Okay. So you're kind of undecided. Undecided. Okay. Are you of the same opinion?
Yeah, we do have the same opinion, but the stronger is no, because we cannot
Fine, realistic. Okay. Okay.
We're also leaning towards no.
Okay. Why?
To say it's realistic would mean to me that it's like can just generally happen under most conditions, but you would need probably very low pressure and very high temperature to minimize interactive forces.
What about okay, so I really love your thinking. Okay, what if you Take the pressure out of the equation. Actually, I want to go back because I don't want to give the answer away. I want to get the vote first, okay? But I will get back with you. Okay, think about the opposite of what you said. Instead of high temperature, okay, all right.
Yes.
Yes, they exist. Why? And give me an example. Okay. Okay. Yeah. Okay. How did you know that? Did you just search for it, or did you learn that viscosity
I just watched some YouTube video about
at some point? Yeah, supercooled fluid. Okay, love it. Can you think of an example in real life? So supercooled fluid is an action we take, right, to cool the fluid. But in nature, where would that happen? Okay, where would that happen? Okay, 30,000 feet. Okay, airplane, 30,000 feet up in the atmosphere. Very cold up there. There's barely any atmosphere left, yet there is fluid flow because the plane is flying. Absolutely inviscid. Very, very good approximation to inviscid. I'll give you a much better example in a minute. Okay, RT. Are you yes or no?
Ours was yes with the condition of our thinking was like a superflow or something because the flow was so fast, powerful that basically just the friction is negligible.
Okay, well, interestingly, you will find that when that happens, actually friction has a significant effect. But it's not the speed that matters. It's the ratio of the speed over the viscosity, which is the Reynolds number. As the Reynolds number increases, which you can increase with very high velocity, you're right. You are right, and we will see this. We will see this when we get to the two-dimensional analysis. What happens? Your equations will have a bunch of terms, and then they will have 1 over the Reynolds number times the friction force. Okay. Now, when the Reynolds number goes to infinity, this term disappears. You might think, but so that's where turbulence occurs. But interestingly, the action of viscous forces is so strong, but it's limited. Okay, but it enhances mixing and a bunch of other things. So, but you're not wrong in high speed flow, but you got to think about the Reynolds number because you got to keep the viscosity down. All right, team in the back. No, why? Okay. Okay. All right. So I'm gonna go back to Nick and link your thoughts to what Passat said about the supercooled. So rather than high temperature, what if you go to low temperature? Okay, when you go home or if you have a laptop now, go and Google fastest winds in the solar system. And you're gonna get Neptune, right? It's got the strongest wind in the solar system. It's got one of the lowest temperatures. Okay, it's a gaseous planet, so very small. I don't even know if it's got a solid core. But the winds on Neptune have been going on for millions of years, pretty much at the same speed from the formation of the planet. So, as the solar system was started kind of spinning due to the action of gravity and the different planetary atmospheres started forming together, there were these inertial forces initially that were, collecting the neighboring gases, and that set off the initial speed at which the planetary gases are moving. And Neptune is still at those same speeds millions of years ago. Because it's so cold, that's where the action of viscosity becomes almost insignificant. So it can happen in real life, in nature. Okay, there's an example. The implicit assumption is actually a very good assumption also in the upper atmosphere, even on an airplane. Okay, yes, there is friction, etc., and drag on the airplane happening. But when we model these things, we can start by staking the flow, assuming the flow to be inviscid. Then we add some effects of viscosity, okay? But in real life, it happens away from boundaries, away from solid boundaries, in the upper atmosphere, you can safely assume the flow to be inviscid, okay? So inviscid flows are realistic, okay? There are some implications of inviscid flows that don't necessarily make sense for things on Earth, such as there's no decay in energy. Like the initial energy is always going to be there forever, which is a reasonable case for Neptune, for example. There is some friction, of course, but over a scale of 1 million years, that is insignificant when you are considering a flow over an hour, right? So inviscid flows are realistic, although viscosity is a property of a fluid and it's always part of the fluid, okay? You can manipulate, the magnitude of that viscosity by cooling the fluid, heating it, etc. Okay? Good discussion. All right. Okay, so next order of business is to convert everything into volume integrals, right? So this guy, like we said last time, we're going to assume control volume to be fixed, so we can get d by dt inside the control volume. This guy is already in volume form. What about this guy? Gradient theorem, right? So remember that integral phi n ds is over a surface is equal to the volume integral of grad phi dv. So this gives us the integral over the control volume. So minus integral of grad p dv. Okay, that's how you get the pressure gradient. Okay, and the Navier-Stokes equation. Okay, what about this guy? It's an interesting integral. Okay. Now remember the integral of u dot n ds. We wrote that as the integral of div u dv. Okay. Now I want you to think of this as your u. Okay. Because this theorem also applies for a tensor. So rho uu is what's called a tensor, right? Because the vector dyadics get 9 components. But this theorem also applies for a tensor. So what happens here, this converts into a volume integral. We're going to talk about this term a lot. But for now, I just want to make sure that the math is clear. Div rho uu dv. All right, what do you think? Can we jump to the differential form now? We got all integrals of the same type, volume integrals. Control volume is, what was the critical step to jump from the integral form to the differential form? Arbitrary. The control volume is arbitrary. Could be this or that or this. So for this to be true for any control volume, then it must be, so for this formula to be true for an arbitrary control volume, then it must be that the integrands are equal. Sorry, I mix different writing notations because I grew up writing, what do you call this, cursive, whatever. I grew up writing this way with all the letters connected to each other. And then I was scolded by my math teacher during my PhD. I was like, this is a terrible way to write. So I started writing this way. And now I combine the two, which is worse. So when you do this, I'm going to write it over here. You get a simplified version, well, not necessarily simplified, a different version of the Navier-Stokes equations, which we call the Euler equations. Those are the governing equations of inviscid flow. So you get d rho u by dt plus div rho u is equal minus grad p vector plus rho g. Beautiful. Historically, the vast majority of the development of fluid mechanics use the Euler equation. The entire field of aerodynamics use the Euler equations. Okay? So these are called the Euler equations for inviscid flows. They apply to compressible, and incompressible flows. For compressible flows, they'll start developing shocks, etc. So we're not going to talk about that, but this term causes shock development. Okay. Now, do not forget, so this is the momentum. Okay, these are the momentum equations. We use the shorthand notation in our group as MOM. Okay. Okay. But do not forget, so this describes the balance of momentum, conservation of momentum. Okay. Don't forget mass conservation, which is d rho by dt plus div rho u equal to 0. Okay. So you have to use those two equations together. Okay. And that's necessary because if you think about it, suppose we fix the density. Okay. Suppose density is constant. Suppose rho is equal to constant. How many variables do we have here? How many unknowns do we have? Number of unknowns. How many unknowns do we have? So what are we solving for, in other words? Suppose rho is constant, you know it. What are the unknowns? Velocity. So how many do we have? 3. Yes. So we've got u, v, w. What else? Pressure. Okay. So you got 4 unknowns. 4 unknowns. How many equations do we need? 4. So this gives you 1, 2, 3, 4. Okay. Number of equations. 3 moms plus 1 mass equal 4 equations. Okay. We're going to get there. Yes. You have to solve both of them together because this one has 4 unknowns in it. You need this equation to essentially complement that. This is mass conservation. So what we do in computational fluid dynamics, we solve these equations without the pressure. And then we do some magic and find a pressure that we'll add to this to make the velocity mass conserving. Okay? But we're not going to worry about that in our analytical derivations. We're going to seek out different ways of working with this system of equations. But yes, you're right. You need these 4 equations together to be able to solve for the 4 unknowns. If the density was unknown, that would add 1 more unknown, so you get 5. Then you would need 1 more equation for the density, okay? So it could be an equation of state, for example, but then that would bring in temperature, so you need an equation for temperature or energy, okay? And then you would close the system. So that would be really for compressible flows, okay? Okay, I wanna talk a little bit about rho UU, and over the years, I've struggled with the best way to explain it, and I always got myself in knots, and you always have this student in the class who calls you on it, like, you know, Louise and Ellie, you know. So to avoid being called upon on any mistake I make, so I'm gonna use a very rigorous and thorough explanation of that term, so I don't get in trouble with you, okay? So rho UU, last time I told you to interpret this equation as what are you transporting? So you are transporting x momentum, so x mom, which is rho u. You're also transporting y mom, rho v, and z mom, rho w. So all you have to do to obtain the x momentum equation is change the transported variable. You get d rho u by dt plus div. You just write rho u, okay? So this is the transported quantity, rho u. This is what is being moved around. In this term specifically, this velocity vector, all 3 components of velocity are gonna move rho u around. Agreed? If you think of rho u as a scalar, think of it as some ink, okay? Ink you call rho u. That ink is gonna move with u, v, and w. Okay, that's called advection, okay? So that's why you fix this guy and you keep this guy as vector, and then this is easily, you can obtain this easily. I'll show it in a second. And then you get minus dp dx plus rho gx, okay? Now this one is simply div of rho uu, rho uv, and rho uw, correct? Agreed? And that's equal to d rho u by dx plus d rho uv by dy plus d rho u w by dz. All right, now I want you to take a moment and do y mom and z mom. Okay, spell it out entirely like this, okay? So again, think about what you are transporting. Okay, for x mom, you're transporting rho u. For y mom, you're transporting rho v. For z mom, you're transporting rho w. Simply plug in that term in the advection tensor and just evaluate the divergence.
question.
Mhm.
If we have a steady state condition, these terms should be cancelled,
Correct.
right? But what is there any condition that, for example, this one cancelled, but these two, we do have this one?
Could have generally, yeah, that could be possible, depending on the condition of the flow. You know,
Okay, so
you could have, I mean, probably not though. But I cannot think of a case where you would have steady state in one direction, and unless, for example, the time scale in one direction is so slow and changes only happen in another direction. So, like, you know, atmospheric size conditions, right? So that could happen. Yeah. Okay. I think most of you got it. Is anyone willing to help me write these down? Yeah. Who would like to help out with Y mom? Any takers? Hafiz? Okay. All right. Okay. So what are we transporting with Y mom? What are we transporting with Y mom?
Yeah.
No, we are transporting rho v, right? Okay. So this means that we have d rho v by dt, correct? Plus div of rho v scalar u vector, okay? Equal minus yeah, which one? dp dy. Yeah, I would like you to use the words, you know, partial p, partial y, or, you know, y pressure gradient, okay? Plus rho g y. Okay, now what about this term? So that's div, right? So we can write it as ddx, ddy, ddz, dotted with, let's spell out the rho vu like we did here. So rho vu, okay, okay, rho vv, rho vw, that's equal. Mm-hmm. 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 Excellent. All right. So you just put this guy in here. That becomes your Y mom equation. Z mom. Okay, we're transporting rho W. So can someone else? Hafiz did a lot of. Hafiz and Nick, you want to take it? Mm-hmm. Mm-hmm. Plus. Mm-hmm. Excellent. Mm-hmm. Excellent. Okay, and then this guy, you can just. Yep. So d rho W u by dx plus d rho W v by dy plus d rho W W by dz. Okay. Okay. Now these terms, these first derivative terms, we call those advection because in general, and you might have learned this or not, in general, advection moves or transports a quantity at the macroscopic level, using a fluid's velocity. So think of advection as a truck moving at a speed or at a velocity u, and that truck is transporting some quantity. So in general, advection always looks like advection looks like grad u phi. Okay. It's a first derivative. Okay. Div u phi. I saw Hayden give me a squint over there. The way to think about this, also think about it in 1D, advection is d u phi by dx. What this is saying that I'm transporting the quantity phi using the velocity u. Advection is always du phi by dx, always. dv phi by dy, dv. Okay. Over here, we were transporting the density in the continuity equation. This is an advection term. We're transporting the density with the velocity vector u. Momentum is more interesting because momentum has 3 components. And each component is a function of the velocity, and it's transported by the velocity. So it's like it's transporting itself, okay, which is really mind-boggling, right? But this is a clean way to think about it. I'm transporting rho u. If I were to call this momentum x, so mom x and mom y, okay, and mom z, this term would be div u times mom x. Okay, so you're transporting mom x with the velocity vector. That's how you think about it. And then substitute. Now, more specifically, you could say here, this is transporting rho u with u, rho u with v, and rho u with w, or rho w with rho u with u, or rho v with u, and rho w with u. Okay, both are valid. Okay, but I like this methodology here. Okay, you focus on, you know, this transient term determines the quantity you're transporting, and you just fill in the blanks. Okay, this is the easiest way to derive those equations. So you only have to think about this one and then expand all of it. You don't need to memorize it. Eventually, it will be second nature if you keep practicing fluids. But if you notice, there's always a transient term, and there's an advection term. For mass conservation, there's nothing on the right-hand side. For momentum, there's forces, pressure, and gravity. Okay? Now think about the transient term. What are you transporting? Over here, transporting all of the momentum, rho u vector. Here, you're transporting mass, which is just the density, mass per unit volume. Okay? Here, momentum per unit volume. Advection of momentum is rho u, u, or div mom times u. And over here, div rho u. Okay? I hope this clarifies things a little bit. I think got 5 minutes. Maybe I can I can follow up on Ellie's question about mass conservation. What I've written here so far, when you have rho, everything inside derivatives, we call that the strong form of the governing equations. Ooh. or the conservation form of the governing equations. Okay, so this form, d rho u by dt plus div, I'm going to write it u rho u, okay? It's just swapping nomenclature is the same, minus grad p plus rho g. This is conservation form or strong form. Okay. Now it turns out that we can simplify this a little bit by using this this equation. Okay. Here's what I'm going to do. Assuming flow is smooth and nice and continuous. The reason we call this conservation and strong form is that this equation is better when used with compressible flows where you have discontinuities. When you have discontinuities, you cannot rip out these derivatives and do chain rules, okay? Because they don't apply, that doesn't apply across a discontinuity. So we keep them in this form and we solve them for compressible flows because you don't have to worry about shocks, etc. But suppose that rho, u, and all of them, all of these are continuous, are nice, continuous, smooth, etc. Then you could say d rho u by d rho du by dt plus u d rho by dt for this term. Okay, you can just chain rule it. Okay, plus this is this is an interesting term over here, and this is a vector identity. This term looks like u dot grad rho u plus rho u div u. Or actually, let me put it in another way. Let me write it another way. U div rho u. Okay, you can tell what I'm after. I'm after the continuity equation. So I need a div rho u, okay? Plus rho u dot grad. What I wrote before is correct, but I want this I want to expose the continuity equation. Equal minus grad p plus rho g. Then you'd come and say, look, if mass conservation is true, then d rho by dt plus div rho u, so that's u into d rho by dt plus div rho u. That's equal to 0. And then you get what we call the weak form, rho du by dt plus rho u dot grad u equal minus grad p plus rho g. You knock out the density, you get minus 1 over rho grad p plus g. And this is we call the weak form. Okay. Now, conceptually and mathematically, this is correct because we trust that mass conservation is valid, has been satisfied, at least to simplify this term. You still need it, however, because you still have 4 unknowns here. And you have 3 equations. You still need that other equation, okay, to close the system. However, we kind of just use the fact that mass is conserved anyway. This should be satisfied everywhere. So we drop out this term. Now, in practice, and when you're simulating these equations, because only in very limited cases do we have an exact solution. In practice, we solve these numerically. I don't like doing this. Because as you are solving the fluid flow problem, what if your mass conservation is not satisfied? What if you're satisfying it up to a little error? You cannot assume it's 0. You have to keep it in and carry out that error with you so that in the next time step, you adjust for that error. Otherwise, you're gonna gravitate towards a solution that's farther away than the solution of the system in the conservation form. Okay? So I always set out to solve the equations in conservation form. Assuming this here assumes that you solve numerically the continuity equation correctly, exactly to 0, which is never true. There's always an error there. If you don't carry that error, it's going to accumulate, it's going to lead you to a different solution. Okay? All right. Thank you. I will see you on Friday.